Welcome to all. Myself, Vinod Kumar Malipudi, Department of Mechanical Engineering, Assistant Professor from SETI Institute of Technology and Engineering, Tadipalligudem. Today we are going to discuss about the Vapour Compression Refrigeration System. It is a very important concept from the refrigeration and air conditioning systems. So let's see how it works. So here, in a short form, we maybe call it as a Vapour Compression Refrigeration System as a VCR. So in order to understand the VCR system in practical, first of all, you must understand what is the ideal cycle on which this VCR system has been designed and constructed. First of all, let us see a Vapour Compression Refrigeration System is an improved type of air refrigeration system where air is treated as a working medium. It's a oldest version of a refrigeration system in which air is treated as a working medium. But nowadays, various scientists and researchers have invented this refrigerator as a working medium. Right. So why we need to call this system as a Vapour Compression Refrigeration System? Why? Because low pressure vapor refrigerant from the vapor is converted into high pressure vapor refrigerant in the compressor. That is why we are calling this as a Vapour Compression Refrigeration System. So as I told, let us see what is the ideal cycle on which this VCR system has been designed and constructed. Basically, there will be 4 different processes on which this ideal VCR cycle has been proposed. So this will be 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Namely, these 4 processes are: during 1 to 2 process, reversible adiabatic compression, or you may call it as a isentropic compression as well, since entropy remains constant during the isentropic process. So during this 1 to 2 process, reversible adiabatic isentropic compression, work done by the compressor will be given as WC equals to H2 minus H1. H stands for the enthalpy. Next one, in the same way, 2 to 3 process, constant pressure heat rejection. So heat rejection usually denoted with the letter QR, which will gives us the H2 minus H3. And move on to the next process, 3 to 4, throttling process or constant enthalpy process. Or even in some sources, this process will also be called by the name isenthalpic process, where enthalpy remains constant. So that is why you can observe H3 equals to H4 during 3 to 4 process. Move on to the last process, 4 to 1, constant pressure heat absorption. So heat absorption is denoted with the letter QA, which will equals to the H1 minus H4. So these are the various 4 different processes upon this ideal VCR cycle works. So let us observe these 4 processes on pH diagram and TS diagram. So this one will be the pH diagram and this one will be the TS diagram. Like I said, during 1 to 2 process, if you observe in the pH diagram, so 1 to 2 process, compression, work done by the compressor. So if you observe here during the TS diagram, as I said, reversible adiabatic or isentropic process where entropy remains constant. So that constant entropy process can easily observed in the TS diagram, 1 to 2 process, where S1 equals to S2. During 1 to 2 process, entropy remains constant. So next one, 2 to 3 process, constant pressure heat rejection. So if you observe in the pH diagram, 2 to 3 process, pressure remains constant, 2 to 3 process, P2 equals to P3. So move on to the TS diagram. So here also you can observe T2 equals to T3. So here I said constant pressure heat rejection. But why the temperature also remains constant? We all know that during the phase transformation, when the refrigerant is rejecting its latent heat, obviously the temperature and pressure remains constant, right? So next one, 3 to 4, throttling process or constant enthalpy process. So 3 to 4 process, I said constant enthalpy. During 3 to 4 process, H3 equals to H4. And the same will be applied to the TS diagram as well, where entropy is slightly changed from H3 to H4. And last one, 4 to 1 process, constant pressure heat absorption, where pressure remains constant and the enthalpy has been increased from H4 to H1. And if you observe in the TS diagram, like I said, during the 2 to 3 process, whenever a phase transformation is taking place, the temperature and pressure remains be constant. That is what here during the 4 to 1 process also can be easily observed, right? So always, in order to evaluate the performance of an refrigeration system, it may be a domestic refrigerator or air conditioning system, coefficient of performance will be calculated as refrigeration effect by the work done. So by considering all the 4 processes, during the 4 to 1 process, usually we will get the refrigeration effect. Why? Because during the 4 to 1 process, we already discussed that the heat absorption has been taking place. Whatever the source which we will usually kept in the evaporator will get absorbed by the refrigerant. So when the heat has been removed from the source, obviously a refrigeration effect will be produced. So refrigeration effect will be gets during the 4 to 1 process, H1 minus H4. And coming to the work done process, we already discussed during the 1 to 2 process, work done by the compressor. So this is the input that will provided for the refrigeration system, H2 minus H1. So overall, coefficient of performance is nothing but the ratio of refrigeration effect to the work done, H2 minus H1. But if you observe here, why I have written in the place of H4 as HF3. H1 minus H4 by H2 minus H1 as H1 minus HF3 by H2 minus H1. Why I replaced H4 with the HF3? You know, if you observe here, I already told you, during 3 to 4 process, it is a isenthalpic process, means constant enthalpy, H3 equals to H4. But here, if you closely observe, point 4 or state 4 lies in the wet region. So if you want to calculate the enthalpy at point 4, you need to know the dryness fraction value at point 4. So in order to bypass the calculation of dryness fraction, you can simply consider the point at saturated line. And this HF3 value can easily get from the relevant temperature limits, right? So overall, coefficient of performance of an VCR system can be evaluated H1 minus HF3 by H2 minus H1. Right. So far we have seen about the VCR cycle. So based on the VCR cycle, if you observe the construction of the VCR system, so mainly it comprises of 4 components. One is a compressor, next one is a condenser, expansion valve, evaporator. So in today's world, all the domestic refrigerator and air conditioning systems have been designed in the same way. Okay, so here, this one will be the compressor, this will be the condenser, this one will be the expansion valve, and this one will be the evaporator. Let us try to understand how a VCR system will work actually. So let us start from here, from the compressor. So from the compressor outlet, the condition of the refrigerant leaving is in the form of high pressure. So high pressure vapor refrigerant leaving the compressor will be delivered to this condenser. So in the condenser, where heat rejection will be taking place to the maybe air or water. Basically, we are having the 2 different types of condensers available. One is a air-cooled condenser, next one is a water-cooled condenser. Since this condenser is provided with the fins, you can understand this kind of condenser is air-cooled. Though high pressure vapor refrigerant, whenever it is entering into the condenser, it rejects its heat to the air and phase transformation will take in place. So remember, during the ideal vapor cycle process, I already told you 2 to 3 process is a constant pressure heat rejection. So the phase transformation taking place inside this condenser under constant pressure means there will be no change in pressure. So the condition of the refrigerant leaving this condenser is high pressure liquid. So before condenser, the condition of the refrigerant is vapor form. After heat rejection, the vapor will be converted into liquid. So that high pressure liquid refrigerant will be later entered into this expansion wall, where expansion will be taken place. So during expansion process, obviously the pressure will be converted from high pressure to the low pressure. Low pressure liquid refrigerant. So that low pressure liquid refrigerant will be entered into the evaporator. So inside the evaporator, where we will keep usually different types of sources. So when this low pressure liquid refrigerant entering into this evaporator, upon absorption of the heat from the sources, so the refrigerant will get boiled and evaporated and will be converted into vapor. So again, the same vapor refrigerant will be entered into the compressor, where further compression will be taking place, later converted into low pressure to high pressure vapor form. So thus VCR system will works. So in the next concept, we are going to discuss about the vapor absorption refrigeration system. Previously, we have discussed about the vapor compression refrigeration system. Here we are going to discuss about the vapor absorption refrigeration system. So let us try to understand what makes the difference between the vapor absorption and VCR system. So in case of the vapor absorption refrigeration system, so the compressor which we have seen in case of the VCR system has been replaced with the following components. One is a absorber, pump, generator, and pressure reducing valve. So these four components will simply replace the compressor, what we have seen in the VCR system. So these four components will play a major role in order to create the refrigeration effect. So here, in order to meet the cooling demand, often the generator which we are going to use in the VAR system will utilize the various heat sources. Like it may be solar energy, it may be fossil fuel flames, and it may be waste heat from the industry effluents or factories. So in order to provide the energy needed for the cooling process. So let us understand how this vapor absorption refrigeration system will works in practice. So here I have presenting a simple VAR system, vapor absorption refrigeration system, in which ammonia will act as a refrigerant and water will act as a absorbent. Means in case of the vapor absorption refrigeration system, we are going to observe two different working mediums which will ultimately going to create the desired refrigeration effect. So here, if we observe the constructional details, one is a absorber, next one is a pump, a generator, a pressure reducing valve, so a condenser, receiver, expansion valve, evaporator. So in the previous VCR system, we have already seen about the working of condenser, expansion valve, evaporator. In case of this VAR system, let us try to understand how this system actually works. So starting from here, from this point 1. So from the evaporator, low pressure ammonia vapors will be entered into this absorber. So whenever it is doing so, what will happen is, so here the temperature will be raised. When these low pressure ammonia vapors entering into this absorbent, and when it is mixed with the absorbent so-called water, so the temperature will be rises. So temperature rises and pressure will be reduced. So whenever a pressure has been reduced inside this absorber, so this absorbent so-called water will allow to draw more amount of the ammonia vapors from the evaporator. So here, but when the temperature rises in the absorber, so obviously absorption capacity of the water will be gets reduced. So in order to avoid that, so simply we are supplying cooling water to this absorber where temperature will be reduced. So here the mixture of water or absorbent and the refrigerant will make a strong solution. So mixture of refrigerant plus absorbent is known as the strong solution. Here, what are those refrigerant and absorbent? Ammonia plus water. So this mixture will be called by the name strong solution, and you maybe call it by the name aqua ammonia solution as well. So this so-called strong solution will be supplied to this generator by means of this pump. So this pump will pressurize this strong solution and will be sent to this generator. So inside the generator, where we are going to supply the heat, it may be in the form of steam, or it may be in the form of heating coil, or it may be waste heat from the industry effluents, or in some situations where relevant energy is not available, you can also make use of the solar energy. So when we supply the enough amount of heat to this generator, where this strong solution will get heated, and ammonia will get easily evaporated and separated from the water. You know, the boiling point of ammonia is minus 33.3 degrees centigrade. So when we supply enough amount of the heat, ammonia will get easily boiled and gets evaporated and gets separated from the water. So upon doing so, when we separated the ammonia from the water, so that solution will be called by the name weak solution. Remember, previously we have seen strong solution is a mixture of both ammonia vapors and the water. So in this case, weak solution is nothing but the simply water or absorbent. So whatever the ammonia evaporated will get supplied to this condenser. So usually it will be in the state of high pressure. Though high pressure ammonia vapor will be sent to this condenser, where inside the condenser you are going to supply cooling water. So inside the condenser, the heat exchange or heat transfer will take place between the high pressure ammonia vapors and this incoming cooling water, and phase transformation will take place. So vapor will be converted into liquid ammonia. So that high pressure liquid ammonia will be next supplied to this receiver, where this receiver will behave or serves as a storage tank. So later that liquid ammonia, high pressure liquid ammonia, will be passed through this expansion valve, where pressure will be reduced. So here the question arises, why do we need to incorporate this expansion valve here? So in order to maintain the low pressure in the evaporator, in order to improve the absorption capacity of the heat, so you should maintain the low pressure. That is why before sending the liquid ammonia into this evaporator, the pressure has to be reduced. That is why the expansion valve has been placed here. So after absorption of heat from the various sources, the ammonia, liquid ammonia, will be converted into vapor ammonia. So thus the cycle will be completed and again started. So that's all from the vapor absorption refrigeration system. Thank you all.